In work, it is parallel. So this is how we define it in O levels. And the next one is mass is given as 0. Mass of the flag is 0.35. The flag is raised to the height of 6 meters. The gravitational field strength is 10. Calculate the increase in gravitational potential energy. Increase means delta GPE. Formula is mg into delta H, which means mass 0.35 times the value of G. If it is given 10, we'll use it as 10. Delta H is 6. So whatever you get is your final answer. Okay, thank you. 21 joules. The unit is joules. And then we have the next one. So the increase in gravitational potential energy of the flag is 21 joules. What does that mean? When the flag moves from here all the way up there to a distance of 6 meters, here the gravitational potential energy was 0. At the top, the gravitational potential energy is 21 joules. So where does the flag get the energy, gravitational potential energy from? Who provides the flag the gravitational potential energy? Is this fellow over here. She does the work on the flag, and the work is converted into the form of gravitational potential energy. Now, can you guess the amount of work she would have to do in order for the flag to get 21 joules of GP? How much work needs to be done by this girl? It's very good. So we assume that if she does a work of 21 joules, that work done is stored in the form of gravitational potential energy. Let's say what the question is. Why the work done on the rope is larger than the value calculated. What is the calculated value? 21. So the question here says that the work done by this girl is more than 21 joules. So probably 25 joules. Why does she need to do some extra work? Any guess? Absolutely. So there could be friction, there could be some energy lost in the form of heat. All right. A child swings backward and forward several times, starting at the highest point A. So this one was the initial point. This one. Explain how another child can obtain an accurate measurement of the time for one complete oscillation. So what is a one complete oscillation? This person started off from the position A, goes to the extreme other side, and gets back to the same starting point. So it starts from here, goes all the way over there, then stops here momentarily, and then comes back to the same starting point. What is that? That is one complete swing. So what do we need to do? The student, he needs a stopwatch. You need to phrase it properly. I'm just writing the bullets. He needs the stopwatch, and he needs to measure the time of 5 swings, and then whatever the time of 5 swings is, he need to divide the time of 5 swings by 5. That would be the time of one oscillation, or cross multiply. Can someone tell me what is the reason for not finding the time of one swing directly and rather going with the time of 5 swings? Yeah. So the more the number of swings, I mean 5 is just for the reference. It could have been 10 swings also. The more the number of oscillations, the more the number of cycles, there is less uncertainty or less error, in simple words. So you obtain a more accurate value if you increase the number of swings. We don't rely on a single one. There's a very good chance that he is not able to start the stopwatch at the right time. He is not able to stop the stopwatch at the right time. So we'll measure for at least 5 swings and average out everything. Calculate the mass of the child. She loses 240 joules of gravitational potential energy. So the change in the gravitational potential energy is 240 joules. What is the formula of change in the gravitational potential energy? It is mg delta h. So this one is 240. Mass is, we don't know. G is given as 10, otherwise we use 9.8. Delta h means the vertical height, 0.6. So 240 times 240 divided by 6, 40. Yeah, I think we get 40, right? So 10 times 0.6 would be 6, and then 240 divided by 6 would be 40 kilograms. So usually in the ideal case situation, the loss in GPE should be equal to the gain in kinetic energy. The loss in GPE should be equal to the gain in kinetic energy. So if she loses 240 joules of GPE, that should have been converted into kinetic energy, because energy cannot be destroyed. But the question is, why kinetic energy at B is not equal to 240? So B is the point where GP is 0, because height is 0. GPE, gravitational potential energy, is 0. Now technically all of the gravitational potential energy should have been converted into kinetic energy. So kinetic energy at B should have been 240, but it's not 240. Let's say it's 200. Question is once again the same. Why is it not equal? Why is it less than 240? What could be the reason? Kinetic or GPE? Oh, kinetic also, yes, because it's being converted simultaneously. So some of the energy, you can write for either, some of the energy is lost to the surrounding in the form of heat, So here we have the next question. A lorry of mass 4.4 into 10 raised power 4 travels along a straight horizontal road. Calculate the kinetic energy. The formula is for kinetic energy is 1 over 2 mv square. So 1 over 2 as it is, which means 0.5. Mass is how much? 4.4 into 10 to the power 4 times the square of the speed, means square of 20. What do we get? All right. So this one says, say the formula that relates the work done to the braking force. So the formula is pretty simple. Work done to the braking force equals to the braking force times the distance in the direction of the force. The braking force times the distance in the direction of the force. So the distance is given by what expression? Is there any expression given for the distance? No. So we'll just write it as it is. Calculate the braking force exerted by the lorry. Stopping distance. But we need to write the expression. उसने क्या state the formula. So we're not supposed to insert the values or calculate anything. Calculate the braking force exerted by the lorry. So work done to the braking force, work done by the braking force equals to F into D. And how much work is done? As it slows down, the kinetic energy of the lorry decreases to 0. The kinetic energy decreases as the work done by the braking force exerted to the lorry. So what does that mean? It means the kinetic energy is now being converted into what form of energy? Or it is being used, or the kinetic energy was decreased by the braking, work done by braking. So think about it this way. This is a vehicle. And it's moving forward. How much kinetic energy is being possessed by this vehicle? 8.8 into 10 raised power, how much was that? 10 raised power 7, 6. 8.8 into 10 power 6 joules of kinetic energy is being possessed by this vehicle. Question is, if we want this vehicle to stop, how much work has to be done by the braking force? How much work? How many joules? Okay, so greater than this, if we suppose that there is loss, some of the energy is lost to the surrounding in the form of heat. But what if there is no energy loss? In that case, can we say the same as the kinetic energy? If there is no loss, so just think about it. Someone is trying to stop this vehicle with a force. How much energy needs to be supplied? At least equal to this one. At least. But should have been more if some of the energy were wasted. In this question, there is no indication that the energy is wasted. So we assume the entire work done by the braking is used to decrease the kinetic energy to 0. So work done by the braking force in this case is equal to the kinetic energy. How much is the force? We don't know. How much is the distance covered in the process? 40 meters. So force equals to 8.8 into 10 to the power 6 divided by the distance 40. What do we get? 22 and 4 zeros. Uh, Electric kettle, the energy supplied to the kettle in 1 minute is this much. Okay. Table is kind of tricky, but just let me get straight to the data, to the first question, should I say. So the first one says calculate the efficiency of the electric kettle. Efficiency means the useful output divided by useful output energy divided by total input. Expression, the formula has to be written as it is. So at least in case you make a mistake, you should be at least getting the C1 compensation mark, which is a mark for the formula. Okay, efficiency equals to useful output divided by total input. Now, what is the useful output by the electric kettle? This is the input that you're feeding the kettle. So this is the kettle here, the electric kettle, and the input that is being fed to this kettle is 120,000 joules. As the output, how much energy is being delivered by the kettle to heat up the water or to the water? Only 95,000. So efficiency would be output divided by the input multiply by 100 if you want to write in percentage. Otherwise, you may not even write in percentage. What do we get in decimal? Okay, 79%. We can write in percentage, or we can also write in decimal. In decimal, the answer has to be less than 1. In percentage, the answer has to be less than 100. Anyway, the next question is calculate the useful power of the gas heated kettle. Okay, so useful power equals to useful work or the useful energy divided by time in seconds. So what is the useful power by the electric kettle? Sorry, by the gas heated kettle? 90,000. What about 130,000? What about this number? This is the input. So the output is 90,000, which is being delivered in how much time? In 1 minute. So energy is 90,000 and the time is 1 minute, which means how many seconds? 60. So what do we get? 1500 watts. Okay, now probably link with the thermal. Both kettles contain the same mass of the water. Okay, so both of them contain the same mass of water. Let's just assume the water is spilling out also. At the same initial temperature is also same. Stene explain which kettle brings the water to boiling point first. So both the kettles have the same mass. Both have same mass. Both have same initial temperature. Let's say 25. Which one would boil the water first? Can I say the one that delivers more energy? Or should it be the one? Yeah, so which one delivers more energy? Electric kettle. Yeah, first one. Electric kettle because it delivers more energy, irrespective of the input. I mean, we don't really care about the input. You might have been supplying, let's say it's 120,000. Let's say even you were supplying 400,000 and it's giving only 95,000 as the output. Efficiency is low. But which one would boil the water first? The one which has greater output, the one that produces more heat energy, not the one which is more efficient. We don't care about the efficiency in this case. Efficiency would affect the cost, the pricing, the consumption of the power, the tariff, the electricity bill, and all that. So it is electric simply as it delivers more energy per minute or per second compared to the first one. Sorry, compared to the gas heated kettle. Okay, just the last one. The boiling water produces steam at 100 degrees Celsius. State one difference between molecules in steam and molecules in the boiling water. Okay, interesting one. Anyone who can differentiate molecules in a steam and the molecules in a boiling water. How much is it? And steam. Steam is not even formed below 100. No. If let's say if the temperature is normalized, if the temperature is decreased again, it means the steam would then be condensed into water vapors. So it's no longer a steam. It has to be beyond 100 or beyond, only then it can be steam. So boiling water, the thing is, boiling water is the liquid water which is being boiled, which is being converted into steam. And steam is when it is converted, all of it is converted into vapors, gas. What is the difference between the liquid and a gas in terms of molecule? Can you give me one difference in terms of spacing between molecules? So which one is gas in this case? Steam. Steam molecules have more spacing. Greater spacing among the molecules compared to the molecules of the boiling water. You need to phrase the question properly.